Okay, today's lecture is finding derivatives of exponential functions. The first one we look at is your basic exponential function, which is e to the x. And the derivative of e to the x is e to the x. Huh? That's the easy one to remember. It's the function whose derivative is itself. Now, if you remember what we used exponential functions to model, this makes perfect sense. Exponential functions model population growth. Population growth is based on the actual size of the population as it is growing. All right? The more things you have, the more babies they have. Right? And so as the curve gets steeper, the slope of the tangent line gets steeper, but we now know here that the derivative is itself, so you can always find the slope of the tangent line of this function by just looking at the actual value. Okay? So the derivative of e to the x is e to the x. Example 1, find y prime when y is equal to 8 times e to the x plus x to the 8th. So here, zoom in a bit. So here we have y prime is equal to, the first one is 8 times e to the x. So the derivative would be 8 times e to the x, because the derivative of e to the x is e to the x. Plus, in the second part, we have x to the 8th. That one is the old product of the old power rule. So we take the derivative by bringing the 8 down, lowering the power by 1. So the whole derivative here is 8 e to the x plus 8 x to the 7th. Okay. Example 2, find y prime when y is equal to x squared times e to the x. So overall, I have two functions that are being multiplied together, so therefore I need to use the product rule. Yeah, we've got to use the product rule. So the first piece is x squared, so the derivative of x squared is 2x. For the second piece, we leave that unchanged, e to the x, plus the derivative of e to the x, which is e to the x, times the first one unchanged. So it's e to the x times x squared. Now, traditionally what we do is we factor out e to the x and put it on the back side. And then the front half is polynomial in descending order. So it would be x squared plus 2x. For example 3, we have y is equal to e to the 4x. This one is going to involve the chain rule, okay? Because you're no longer taking the derivative of e to the x, it's e to some other function. That other function serves to be the inside of the composition. Okay? So we would have y prime is equal to, and then you think about the general derivative, e to the 4x. Well, the derivative of e to the 4x would be e to the 4x, but because it wasn't just x, it was 4x, we multiply that by the derivative of 4x, which is just 4. Okay? So this inside piece right here, this exponent, is the inside piece, right? And if you're thinking about the chain rule, it's the g of x. Okay? Now, normally we write this with the 4 in the front. In example 4, we want to find dy dx when y is equal to e to the 3x power divided by x cubed. So dy dx is equal to, now to take this derivative, we need to use the quotient rule. So it's going to be the derivative of the top. So the top is e to the 3x, so that would be e to the 3x times 3 because of the chain rule. So here again is an instance of we use the chain rule because we had to. All right? Times the bottom unchanged, so times x cubed, minus the derivative of the bottom, 3x squared, times the top unchanged, divided by the bottom squared. The bottom was x cubed. When you square x cubed, you multiply the exponents, and you get x to the sixth. In the next step, we're going to factor out as much as we can. So I see that both terms on top have a 3. The left term has x cubed. The right term has x squared, so I can factor out x squared. And both terms have e to the 3x. So that leaves me on the left with an x. And on the right, I factored everything out, so I need a placeholder of a 1. And then divide by x to the sixth. And then the last thing we can do here is cancel off the x cubed and make that x to the fourth. So we get 3e to the 3x power times x minus 1 over x to the fourth. Now, to do the derivative of an exponential in general, where it's just a as the base, the derivative is a to the x times the natural log of that base a. Okay? So the first thing I want to show you out here on the side is that this does not conflict with our special case of e to the x. Because if I were to find the derivative of e to the x, and I use the new rule here, that's the general rule, then the derivative would be e to the x times the natural log of e. But what's the natural log of e? 1, all right? So this is just e to the x, which is what we already know. The derivative of e to the x is e to the x. Okay? So e to the x is just a special case of this general rule. Okay? So this is the one you could always use. It's just that the natural log of e is 1, and so we have a special rule for it. Okay. Let's look at example 5. The function is y is equal to 2 to the x. We want the derivative. So this would be y prime is equal to 2 to the x times the natural log of the base, which is 2. And that's it. Let's look at example 6. The function here is y equals x times 7 to the x. So again, I need to use the product rule. And this is going to be the derivative of the first one. So the derivative of x is 1 times 7 to the x power unchanged plus the derivative of 7 to the x, which would be 7 to the x times the natural log of 7. And this is all one big thing right here. Times the x. Now usually to make sure that the limits of the natural log are known, we put parentheses. So it's natural log 7, and it's not confused with natural log of 7x. Okay? So this piece right here is the derivative of 7 to the x. All of it. There's no chain rule involved in that one. It's just, that's the formula for the derivative. Okay. And then you could simplify that a little bit. Take out the 1 and stuff, but that's usually as far as it goes. All right, questions over example 6?
So the answer just stays 7 to the x plus...
Yeah, you probably simplify it, but get rid of the 1, but then it would just be 7 to the x plus 7 to the x natural log of 7 times x. Yeah. Okay, example 7 is find the derivative of y equals 3 to the square root of x. So this one is going to involve the chain rule. Let's watch this now here. So y prime, the first thing I need is the derivative of the exponential, 3 to a power. So the derivative of 3 to a power would be 3 raised to that power times the natural log of 3. It's the natural log of the base. But now, the power was not just x. And because of that, I have to chain on the derivative of that power. So the power was the square root of x, so I chain on that derivative, which is 1 over 2 square roots of x. And that's it. You could leave it like that, or you can combine it into like one big fraction. But they're all multiplied, so it's not going to change anything. Okay? But reiterating, because the exponent is not just x, you have to multiply by the derivative of the exponent. So it's the derivative of the square root function, which is 1 over 2 square roots of x. All right, let's look at example 8. Now, I've changed the problem a little bit so that you can see how it compares with number 7. This one is y equals 3 raised to the square root of x squared minus 1. So to find this derivative, the overall scheme is exponents. So the derivative of the exponent function is 3 raised to that power. So that's going to be the square root of x squared minus 1 times the natural log of the base and now by the chain rule I have to take the derivative of the exponent. So we're going to end up taking the derivative of the square root of x squared minus 1. So from here on out, it's the derivative of the square root of x squared minus 1. Well, the derivative of the square root function is 1 over 2 times the square root of the inside. Now, what do you notice about this inside? Yeah, it's not just x either. So in the process of taking the derivative of the exponent, I have to use a second chain rule. This is why it's called the chain rule, because you keep chaining on derivatives, like links to a fence, right? Now I look at the inside of this function, which was x squared minus 1, take its derivative, and you get 2x. Okay? So do you see the chaining of the derivatives, right? You're just tacking them on until you get to the inside where you have completely taken that derivative. Okay? And the only thing you can do here is cancel some 2's and write everything as a fraction. So it's going to be 3 raised to the square root of x squared minus 1 times the natural log of 3 times x over the square root of x squared minus 1. Example 9, the amount in grams of a radioactive substance present after t years is given by A of t is equal to 1200 times e to the negative 0.1 t power. Find the rate of change in the amount present after 6 years and interpret. So anytime you're looking for rate of change, that tells me you want the derivative. So we need to find a prime of t. A of t is 1200 times e to the negative 0.1 t. So that would be 1200. Now I need to take the derivative of e to the negative 0.1 t. So that would be e to the negative 0.1 t times the derivative of the exponent, which is just negative 0.1. Okay. Now this is an e to the t power, so that's our first rule, where the derivative is just e to the t, period. Okay. There's no natural log stuff here, because it's the e one. Okay. Now this I would simplify. 1200 times negative 0.1 is negative 120, e to the negative 0.1 t. Next, it says find the rate of change in the amount present after 6 years. So that would be apply the derivative, apply 6 to the derivative. So this would be negative 120 e to the negative 0.1 times 6. If you calculate that, you get negative 65.857. And the units would be grams per year. For the interpretation, we would write out a statement. The amount of substance, the amount of the substance is decreasing at a rate of 65.857 grams per year after 6 years. Okay. So you just want to make a complete sentence statement. Notice how I took the result. The result was negative, and I turned that into verbiage. I said that the amount of the substance is decreasing at that rate. So if it's negative, it's decreasing. If it's positive, it is increasing. Okay. Example 10. The weight of a cow in pounds is based on its age in months and can be modeled by W of t is equal to 500 times 1 minus e to the negative 0.04 t, and then that quantity cubed. We have three things. Find the weight of the cow after 36 months. Find the rate the weight of the cow is changing after 36 months and interpret. And C, determine what happens to the weight of the cow over time. Okay. So in the first part, we just want the weight of the cow after 36 months. So that is not a derivative. That's just the regular straight-up function. So we would do W of 36. This would be 500 times 1 minus e to the negative 0.04 times 36, and then that quantity cubed. Now remember, the only thing that's being cubed here is this expression from 1 minus e to that power. The 500 is not being cubed. 500 is multiplied on after the fact. All right, if you work this out, you will get 222.16 pounds. Pounds. Part B says find the weight of the cow is changing after 36 months. So for that we would need the derivative. So this is going to be W prime of t. Now we have to break down the W function. This is 500 times a function cubed. So you can use the power rule. Okay, bring the 3 to the front and multiply it by the 500. You can either do it in one foul swoop, or you can write out the 500 and then do the 3 part. That's what I'm going to do here. Okay, times 3 times when you do a power rule, you leave the inside the same. You decrease the power by 1, so now the power is 2, and you use the chain rule. And the chain rule here, you have to multiply by the derivative of what was inside of this baseline here. So this would be times, and now I'm out of room, so I'm going to do it over here, times the derivative of this inside. The derivative of 1 is 0. The derivative of negative e to the negative 0.04t is negative e to the negative 0.04t. Now for that one, because the exponent was not just t, I have to chain on yet another derivative. So we're going to chain on the derivative of the exponent, which is negative 0.04. Okay? So this one had an inside, which was 1 minus e to that power. And then the 1 minus e to the power had an inside, because it wasn't just your basic t. So we have to just keep chaining these things on.
Question.
Mm-hmm.
When we get to the e part, you're getting the derivative of only the exponent, right? So e is like it went away for that last part.
This piece right here is the derivative of the exponent alone. This piece is the derivative of the 1 minus e to that power. Exactly. Okay. All right. Now to simplify, let's multiply the numbers together. So what numbers do we have? We have 500, we have 3, and we have negative 0.04. All of those numbers are going to get multiplied together and put up in the front, and that actually turns out to be 60. Then I'm going to take this piece, and that's 1 minus e to the negative 0.04t quantity squared. And then I'm going to pick up on this piece, which is negative, oops, not negative. The negative was already taken with the numbers. Those two negatives cancel. So that is the function. That is the derivative. Okay? So make sure you know where all these parts went. The numbers combined to give us a positive 60. That includes the negatives that were just sort of being multiplied there. And then I have the rest of the part, the square part, and then the extra derivative part. I cannot combine this derivative part into the square because the squaring takes precedence, right? Squaring over multiplication, order of operations. Okay. Now, let's find the value of the derivative after 36 months. So that would be 60 times 1 minus e to the negative 0.04 times 36, quantity squared, times e to the negative 0.04 times 36. And if you work all that out, you get 8.277 pounds per month. I'll leave you to write the interpretation, but it is basically that the weight of the cow is increasing at 8.277 pounds per month when the cow is 36 months old. Okay, so at 37 months, we would expect the cow to weigh about 230 pounds, right? Because we had 222, we're adding 8 pounds a month. Cow's going to weigh about 230. Okay. All right, the last part is determine what happens to the weight of the cow over time. when you see this kind of phrasing, what they are asking for is the limit as t goes to infinity of the weight of the cow. Okay. Now, so basically what you're looking for here is the limit as t goes to infinity of the original function, 500 times 1 minus e to the negative 0.04t cubed. Okay. I'm going to show you a method that you can use that will make taking this limit straightforward. Okay. What you do is you start with the most inside part of the function where the variable is, and then you work your way out. Okay. So here we go. So as t goes to infinity, what's the first thing you do to a t value if you were going to figure out this value? You would multiply it by negative 0.04. Okay, so as t goes to infinity, negative 0.04t goes to where? It's going to go to negative infinity. Because if t is going to positive infinity, if I multiply it by a decimal, it's still going to go to infinity, it's just not going to go as fast. But if I multiply it by a negative number, that is going to switch the direction that the t values were going, right? So now, instead of going to infinity, they are going to negative infinity. The next piece of the puzzle here is e to this power. We want to know where that goes. To figure out where this goes, you have to remember what the function y equals e to the x looks like. It's the exponential, and it looks like this. Okay. You have to understand the role. Negative 0.04t is the exponent. The exponent in the graph is x. In the previous line, we know that the exponent is going to negative infinity. So when the exponent goes to negative infinity, we are going to the left, and the y values are going to 0. So this is now going to 0. Okay, it's the horizontal asymptote of that. Now notice, I didn't even have to think about the negative 0.04 and the t and all this sort of stuff. I'm just thinking about it bit by bit, piece by piece, and I know that that's the exponent, and so when the exponent goes to negative infinity, this whole thing goes to 0. Yes?
How do you know that it's going to the left?
The negative 0.04t is the exponent. The exponent in the picture is x, and so it's going to negative infinity. So we're going to negative infinity, it goes to 0. Okay. Then we have, the next piece is 1 minus e to the negative 0.04t. Well, if e to the negative 0.04t is going to 0, 1 minus that must be going to 1. Then we are going to cube that. If you cube 1, you still get 1. And the last step is if you multiply it by 500. Then all that goes to 500. Okay? So you're just acting these expressions out. Okay? So the ultimate statement here is the limit as x goes to infinity of w of t is equal to 500. In essence, that means as time goes on, the weight of the cow is going to approach 500. In particular, this function is always increasing, so the weight of the cow approaches 500 over time, but it never goes over 500. So 500 is sort of the maximum weight of the cow.